Okay, guys, section 2.6, exact equations. What are exact equations? Well, remember we had in the first class classification implicit functions and equations with implicit solutions. Imagine that there is an implicit function given. X squared plus x y squared equals 5. Sometimes it can be solved for y. In this case, it can be solved for y, but not always. Let's create a function of two variables, phi of x and y, and just copy our left side. Well, a function of one variable, there are functions of two variables, remember from calculus 5c, right? So what is this equation actually if we consider a new function we just created, x squared plus xy squared? The equation is actually going to be equal phi of xy equals 5 equals a constant. Function of two variables equals a constant. That's my equation, implicit function, right? Now guys, I'm going to differentiate d phi by dx. So I'm going to differentiate actually this equation, but because just like equation is phi equals 5, so derivative of phi is 0, and it's not going to be too difficult for me, right? So how do I usually do this? Well, when function depends on two variables, I differentiate phi by the first variable partial derivative, right? And then differentiate phi by the second variable partial derivative. And then I see that my actual y, it's actual function of x, and I'll need to differentiate y of x. And derivative of 5 is going to be equal to 0. So if I differentiate this equation by dx, I'm going to get this expression. Now let's apply this expression to our function. Now I'm going to just normally differentiate it as a function of x and y. So first I'm going to differentiate it pretending that it's just a function of x, right? Remember that d phi dx, it's a derivative by x of this, and that's 2x, right? What is derivative by x of this? That's y squared, right? We're kind of considering y as independent variable here. It's dependent, but we are assuming that it's independent for differentiation purposes. d phi by dy. Okay, there is no y, so derivative is 0. Here, it's going to be x as a constant for us because of two variables. If we differentiate by the second one, we assume that the first one is a constant. And here we are going to have 2y. Now let's plug it into the formula. We have 2x plus y squared, that's my first derivative, plus 2xy. Well, I rearranged a little bit my factors, but that's actually. And then dy dx. I don't actually know what is y, so I just write it down like this. Well, guys, what we see right now, it's a differential equation. And because we got this differential equation by differentiating of this equation, that's going to be a solution. So solution is phi of xy equals 5, or this implicit function. And if our major goal during this section is going to how to get back from equation, if somebody gives it equation like this, how to get to this one. Well, equations which can be obtained from implicit functions by differentiation are called exact equations. So what is interesting for my equation, for example? Because we have two partial derivatives and the function of two variables. I remember that in calculus 5c we had something like we called Clairaut theorem, which was telling us that second partial derivatives of second mixed partial derivative is supposed to be equal. So if you differentiate the function by x and then by y, or you differentiate function by y and then by x, the derivatives are equal if they're continuous. So what I'm going to do, guys, I'm going to call this function m of x. Just set it up like this. And this function n of, well, I should call this n m of xy actually. Why did I just let it be xy? Here can be also x and y, right? So these are first partial derivatives. I know that this one is derivative by x. So if I differentiate it by y, the derivative is supposed to be equal the derivative which was by y by x. And this is condition which is going to assure us that this equation is exact. So that somebody took an implicit function and differentiated it as like function of two variables and got this equation. I'm going to check this condition for this equation, but not necessary because we already kind of obtained it this way, right? So what is my? What is my? If we differentiate this by y, we are going to get 0 and 2y, right? What is nx? If we differentiate this by x, we are going to get 2y, and they are equal. Again, we are checking the fact here that d phi second derivative by dx dy equals d phi second derivative by dy dx. Well, if function phi exists, then this must work. So that's going to be our check if we should go back and search for function phi, which is going to be like function like this. Okay? So if this statement is true, then the equation is exact, and we can actually kind of use these two derivatives to go back and find function phi. How? Well, let me show you on this one and then move to real example. So if you know that function of two variables, x and y, the derivative by x equals 2x plus y squared. How do we find function phi? Well, you integrate this by x, right? 2x plus y squared integrate by x. Consider y as a constant. We have what? X squared. We integrate this plus yx plus a constant which can depend on y because we are differentiating by x. Constant can depend on y. Now, d phi dy. What is d phi dy? This is d phi dy, or this one is d phi dy. What is d phi dy? I'm going to put over here m and over here n. In the book, they like to name it m and n, but for the beginning, it's nice to understand actually what they are. D phi dy equals 2xy. So let's check what is phi then. We have to integrate it back by y to find out what was phi, which we differentiated by y, right? Remember that x here is a constant. So we have 2x y squared over 2 plus a constant of x. Canceling 2, we are going to have x y squared. What I'm thinking I'm missing a square over here, right? It was y squared x. Now, I'm going to compare these two. If my equation is exact, these two must match each other. Well, maybe the constant is going to hide a term inside, which depends only on x or on y, but the terms which depend on both x and y are supposed to match. Look, this term and this term are exactly the same, right? X squared can sit over here, and there is nothing which depends totally on y. So my function phi is x squared plus y squared x, and it's supposed to be equal a constant, right? Because when we differentiate this phi, we are going to get a 0 here. 0 is produced by a constant. We don't know whether it's 5 or not 5. Actually, specific number 5 will be given by initial conditions, but otherwise we solved our equation. We found the function which we differentiate and get this equation. Now, example. So that was artificial example because I actually started with a solution and went to the equation and then back to the solution. Now, actual example. Well, guys, I don't know how more convenient is to label the functions, right? You understand that this is derivative by x of some function phi. I'm going to label it d phi dx. In the book, they always will label it with some other letter, either m or m, and you can do it too. I'm going to also put m over here. This one is d phi dy, and I'm going to label it as letter n. Well, I think labeling with derivative is better because it tells you what to do with this one, right? But, well, I don't know. We remember that my, which is d phi second derivative dx dy, is supposed to be equal to d phi second derivative dy dx, right? I think over here is supposed to switch them, but that's okay. The point is, so that's, I think that's n of x and this is m of y, but that's okay. Still this, they're supposed to be equal. So you differentiate this by y and differentiate this by x, and you're supposed to get the same number. If you get the same number, you can continue solving. If you don't get the same number, maybe you're supposed to kind of play a little bit with this equation. So let me kind of do the check. So my, which is d second derivative phi dy dx. Here I'm supposed to switch them. This one comes like last one. So I'm differentiating. This is already derivative by x, so I'm differentiating it by y. So 3x, right? If I differentiate it by y, plus 2y differentiated by y. In x. Well, I'm going to just write down an x differentiate by x. That's 2x and just y. Does not look like we are dealing with exact equation. Well, shall we give up? Equation doesn't look like exact. That's 3x and 2y, and that's 2x and the y, right? It's kind of 1 unit off everywhere. Well, we are going to postpone solution of this equation for a while, okay? And maybe move to one which is exact. So this one is not exact. I'm going to write down not exact. Okay. As I said, we're not going to give up on this equation, but we are going to consider it a little bit later. Let's now consider a simple example of exact equation, show how to find solution, and then return back to this one, which is not exact, but very promising, right? Okay, let me move to a different page. So, so my next equation, example 2, oh, sorry, it was a little bit off. No, it's visible. Okay, shifted it too much up. So let's check if this one is exact. Again, whatever does not have a derivative, it's a derivative by x. So we'll need to differentiate it by y. Well, let's name it m. So my. This one is 0, right? If you differentiate this by y, it's negative 2x. Differentiate this by y is 0. This is, let's call it n, and nx. Differentiate this by x because we kind of, that's derivative by y already, right? And we need x and y, like mixed derivative. So this one by x is 0, right? And minus 2x here by x and 0. Well, looks like they are equal, this one and this one. So it's exact equation, we can solve it. Well, again, guys, depending on like how you like to solve something, you can solve it like how the book suggests to do this, or how I do this. I usually going to write down d phi dx equals 3x squared minus 2xy plus 2. And then write down what is phi then. Integral 3x squared minus 2xy plus 2 dx. Considering y as a constant here, I'm just going to integrate it by x. It's a partial anti-differentiation, what I'm doing. So I have 3x cubed over 3 for this one, right? If I integrate by x over here, it's 2x squared over 2y. and 2x plus a constant which can depend on y, right? Because we are integrating by x or differentiating by x, there can be a constant depending on y. I'm going to cancel this and this and this and get very like nice solution. X cubed minus x squared y plus 2x plus a constant of y. Can be a whole function of y, but no function of x. Now I'm going to write down d phi dy equals 6y squared minus x squared plus 3, which means that phi is going to be integral of 6y squared minus x squared plus 3 dy, and I'm going to anti-differentiate it by y. Again, when I do this, I'm assuming that x is a constant. So 6y cubed over 3, right? Square is going to give me a cube. This is a constant, so I'm just going to multiply it by y. This is a constant, I'm just going to multiply it by y and add a constant which depends only on x, right? Well, going to simplify it a little bit. 6 and 3 is going to give me 2, right? 2y cubed minus x squared y plus 3y plus constant of c. Now I'm going to compare these two and kind of obtain one function. So what I see the same term here and here. I'm going to copy it. Minus x squared y. Do I see more same terms? Doesn't look like. I do see x cubed and 2x here. They can hide in this function. So I'm going to write them down. X cubed plus 2x. And I do see 2y cubed and 3y, which can hide in this c of y, right? I'm going to add them too, and that's my final answer. Well, usually, guys, remember that equation is phi equals a constant. I'm going to put constant here, and this is numerical constant. If you do know the point, like initial point, when x, for example, equals 1, y equals 3, then you can calculate this constant that is going to give you an equation like we had in the beginning. But if you don't, you're just going to keep your final answer like this. It's not necessary to solve it for y, and most likely you won't be able to do it. Okay? Well, solution does not look very nice, but that's a solution. You differentiate it, you get your equation. Now, guys, what should we do if equation is not exact? Well, we're supposed to try integrating factor when equation is not exist. And what is integrating factor? It's a function mu, right? Because we have two variables here. It's going to depend on two variables, x and y. And let me explain you how to do this. Okay, so now I'm going to teach you how to make exact equation from not exact equation, if possible, of course. Well, let me go back to the first example we had. Remember the function over here, the derivative was 3x plus 2y, and the function over here, derivative this function by x was 2x plus y. Well, it was not exact because these two derivatives were not equal, though they are supposed to be equal if this was a derivative of one function phi, right? So equation was not exact. So what should we do? Well, remember integrating factor is multiplying by some function mu and turning it into like desirable equation. Well, let's see how it's going to look. I'm going to continue on this page, but actually we are continuing this equation. Well, maybe I should keep it over here. So I'm going to do it a little bit more general. Imagine that we have m. Maybe I should write down that it's integrating factor. Integrating. Imagine that we have m dx plus n dy equals to 0. Well, we actually always had m plus n dy dx, right, equals to 0, but I kind of moved dx here. And my is not equal to nx, so it's not exact. Well, that's exactly what we have over here, right? But maybe we multiplied by mu, multiply both m and n by mu, and then m mu y will be equal n mu x. well, we just don't know mu, but if we do multiplication by mu and then differentiate the resulting two functions which are multiplied already by y and by x, if they are equal, well, the equation is becoming exact and we can apply our technique, right? The question is how to find this mu. Well, remember guys that because function m and function n both depend on x and y, mu is going to depend on x and y too. So what I'm going to do, guys, I'm going to do this differentiation. So what we have my by mu plus m mu y, right? Partial derivative by y here supposed to be equal n by x mu, partial derivative by x, and m mu x. Well, let's make assumption. We cannot solve this equation in general because just one equation, but function mu depends on two variables, and this is partial derivative of this mu by y, and this is partial derivative of this mu by x. It's going to be very hard for us to just solve this in general. But if mu is function of only x or is function of only y, which is not necessarily supposed to be true, maybe not true, maybe not true, then one of these derivatives is going to disappear. Well, I don't know. Let's assume that m is just a function of x. M is a function of x. What does it mean? That mu y equals to 0 because it depends only on x. Mu y is equal to 0. So we are going to kind of drop this term and we are going to have my mu equals nx mu and mu x. That's only one derivative, right? Well, what we can do here, I'm going to move all mu's on this side. So m y minus nx mu here and mu x. Now we remember that mu x actually is d mu dx. If it was function of two variables, I would put partial derivative, but because it's a function of one variable, I'm assuming that the first one that does not depend on y. I'm just going to put a straight derivative. So what I can do, I can write it down as normal equation. I'm going to move this over here and in denominator, and I'm going to put d mu, move this mu down, and put dx here. Okay, I don't have space here to put dx. And that's what we are going to have. We can integrate it, right? Get this ln like normal integrating factor and get some function. Let's check if it's going to work in this case. Okay, it's probably not gonna work, but who knows. Well, we already I'm going to consider this example. So we already calculated mn, my, and nx, and we know that these are these numbers, right? We just need to kind of plug everything into this equation and see if mu is going to give us anything nice. So integral my, which is 3x plus 2y minus 2x plus y. I'm subtracting this 2 divided by n. Where is my n? N is x squared plus xy dx. And here integral is going to be what? Ln of mu. I'm just going to write it down. Well, I'm going to simplify this expression. Maybe after simplifying it's going to be nice. Normally, guys, if your assumption is correct, y is supposed to disappear from this equation. If it does not disappear from equation, it means that assumption is not correct. So what I have, 3x minus 2x is just x, right? 2y minus y is just y. And in denominator, if you take x outside of parentheses, you're going to just get x plus y. Ln of mu. Well, you see that x plus y cancel, and we have dx over x, which is ln of x. Ln of x equals ln of mu. Oh, which is very good for us, right? So we can actually say that mu equals x. In general, there is more like a constant and more like, but because we just need one integrating factor, one function, this is going to work for us. Now I'm running out of paper. I'll need to find a new page to write down the rest of the solution. Okay, let me continue on this page, and I'm going to remove this and remove this too. So what we have, we found the integrating factor. Let me bring back my equation which was not working. So let me see, equation is visible. So bringing back equation. So I need to multiply this equation by x, right? My integrating factor mu is equal to x, so I multiply by x. So I'm going to get 3x squared y plus y squared x plus x cubed x squared y prime equals 0. Well, guys, just for fun, I'm going to check if this derivative, if these two derivatives are equal. So y is equal nx. Is it? I always suggest you to do this because you calculate integrating factor, do a little mistake there, and then your solution is wrong. So my, well, derivative by y is 3x squared. Derivative by y is 2yx. nx. 3x squared and 2xy. Well, they're exactly the same. So integrating factor is working. Hooray. Now just apply a similar technique. So we just write down d phi dx equals 3x squared y plus y squared x. So phi, guys, I'm going to just integrate it by x. I don't want to write down the integral, okay? So I have 3x cubed over 3y plus y squared x squared over 2 plus a constant which depends on y. d phi dy 3x squared plus 2, oh sorry, I'm sorry, that's not 3x squared but x cubed, copying from the wrong place, x cubed to not 2x squared y. So I'm going to integrate it. Phi is going to be x cubed y plus x squared y squared over 2 plus constant of x, and I compare these two functions, canceling 3 and 3. I'm going to get exactly the same. X cubed y, y squared x squared y squared over 2. So there is no function which depends totally on x or y. So my phi equals x cubed y plus y squared x squared over 2 and equals to a constant. That's real constant. These two constants are functions of x and y. That's a real constant. Okay. Kind of not very easy, right? But possible to do. I think we can try one more example here. Let me move this up and shift the page up so we can do one more example. Example 3. Y dx plus 2x minus y e to the power of y dy equals 0. I'm asking you to do it yourself. Well, try to check what kind of integrating factor, if it's exact or not exact. And then you can look at my solution. I'm going to count to 3. So I suggest you to stop the video and try to do it yourself. Okay? 1, 2, 3. So I differentiate this by y. y, and that's equal to 1, right? And differentiate this by x, mx, and does not depend on x, and equals to 2. Not exact. Not exact. Well, what am I supposed to do? I supposed to kind of use integrating factor, right? So I'm going to write it down like this. Mu integrating factor by this y and derivative by y of this is supposed to be equal to x minus y e to the power of y mu and derivative by x, right? That's going to be my new n, and that's my new m. Well, I'm going to do the differentiation. I still don't do assumption about mu. So it's mu y by y plus mu, derivative of y is just 1, equals by x. Okay, I'll differentiate this expression first. 2 by mu, and because this one depends on x, this one does not depend on x, plus 2x minus y e to the power of y mu x. So should we do any assumptions? Well, I think I'm going to maybe simplify it a little bit. I have like mu, 2 mu, so maybe I should kind of combine it together and start thinking like what it's like depends on what, on x or on y. I'm going to write mu y by y equals, I cancel 1 mu from this 2. Well guys, what I see, if my mu depends only on x, then this part is going to disappear because it has derivative of y, right? So it's going to disappear like this, 0. But my solution, like d mu dx and mu here, still going to have y, which is not likely. Like remember, under the integral you are not supposed to have functions of y. So maybe I should assume that m depends on y only, but not on x. Then mu x, derivative by x, is going to be 0. And this whole term disappears. Good for us, right? So I have mu y by y equals mu. From where d mu dy equals mu. I'm moving y over here. Well, we got a d mu over mu equals dy over y, from where mu equals y. Well, I'm missing one step here. Ln of mu equals ln of y. Remember, we need just one, so I'm just setting mu equals y. Now we are fine. And we can just multiply by this y. I'm not gonna check it. I have just little space left. Maybe this space is supposed to be used to solve equation instead of checking it back, like whether I'm going to get this derivative or not. Well, again, you would ask probably, how did I guess that it depends only on y, not on x? Guys, usually you just trust your common sense, or you just make assumption. Okay, let's it depend on x. Are we going to get a nice integral of y? Let's it depend on y. Are we going to get rid of x then under the integral? If you don't, maybe it depends on both x and y, and there are going to be the cases where it depends on both. Well, here my integrating factor is y, so I'm just going to apply it. So I'm going to multiply my d phi dx by extra y, and I'm going to get y squared here, right? So phi from here is going to be y squared x plus a constant dy, dy 2xy minus y squared e to the power of y. Not very nice, but okay. Phi equals, integrating this is going to give me 2xy squared over 2. Integrating this, who remembers integration by parts? I'm going to write it down, minus y e to the power of y dy. Well, it's going to take a second, but not too long. Xy squared minus square e to the power of y plus 2y e to the power of y minus 2 e to the power of y and the constant of x, right? Now just one thing to compare this. This expression is exactly the same as this, right? And the whole big expression here can be a function of y from here, right? And that's it, function of y. I think that's it. We got a solution. So that's the whole function is a solution. I'm not going to rewrite it. I'm just going to label it a phi. Cross the constant, it makes equal to c, and that's going to be the final solution. Okay, I think that's all for exact equations. And Just do the homework. And sometimes in the homework problems, they do have a suggestion. Use this integrating factor or that integrating factor. Trust them. Use the factors they are suggesting. Okay? Okay, that's all. Thank you.